we will now look at graphing quadratic equations with two variables. Remember, once we learned about solving linear equations with one variable, we learned about solving linear equations with two variables. In this case, we saw equations in two variables have many solutions, so we needed to graph them. Similarly, we will need to graph the solutions to quadratic equations, y equals ax squared plus bx plus c. While we have not looked at graphing quadratics in this form, we have graphed quadratics in the form y equals a times x minus h squared plus k. This is slightly different from what we want, but we learned how to get from the form we have, y equals ax squared plus bx plus c, to the form we know how to graph in, a times x minus h squared plus k. Here you can see some examples where we did this in the past. This was a long process to be able to change the form, but thankfully we'll be able to find some shortcuts both for graphing and for getting to this form. But before we learn these shortcuts, let's look at what we already know about graphing y equals a times x minus h squared plus k. To graph this function, we'll start with the basic equation y equals x squared, which gives the basic graph of a parabola with bottom point at the origin 0, 0. Now the first move we make is replacing x with x minus h. This will cause a horizontal shift by h, moving our lowest point from 0, 0 to h, 0, because we move by h in the x direction. Next, we multiply by a. This will cause a dilation by a in the vertical direction, making all of our points a times higher. Notice here that we're assuming a is positive, otherwise it would have reflected it across the x-axis. Also notice that making all the points a times higher does not move our lowest point, because our lowest point has height 0 and a times 0 is still 0. Finally, we add k. This causes a vertical shift by k. In this case, we're using k to be negative, so the graph moves down by k. Notice here that our lowest point moves from h0 down to the point hk. And we call this extreme point hk on the graph the vertex. Now that we found the graph for y equals a times x minus h squared plus k, let's explore it a little. Using this graph, we see that the vertex is the point hk, where these are the same h and k from our equations. This graph has two x-intercepts and a y-intercept. And similar to the basic graph y equals x squared, this graph is symmetric. Although unlike y equals x squared, this graph is not symmetric across the y-axis. This graph is symmetric across the vertex. We call this the line of symmetry. It's the vertical line that goes through the vertex, the line x equals h. Now let's bring what we found back to graphing solutions of y equals ax squared plus bx plus c, which we can also think of as the function f of x. To graph this quadratic equation, we need to find these important points that we saw: the y-intercept, the x-intercepts, and the vertex. Like with lines, the y-intercept happens when x equals 0. So if x is 0, then y equals a times 0 squared plus b times 0 plus c, which is just c. So we get that the y-intercept happens at the point 0, c. How about the x-intercepts? Also like lines, the x-intercepts happen when y equals 0, because we're along the x-axis and they're not moving up or down at all. If y equals 0, then we get the equation 0 equals ax squared plus bx plus c by substituting y equals 0 in our first equation. We can solve this now using the quadratic formula. To get r1 and r2, are negative b plus or minus the square root of b squared minus 4ac all over 2a. And once we know these two values, r1 and r2, we get that the x-intercepts are r10 and r20, because the x value is either r1 or r2, and the y value is 0. Remember, depending on the discriminant, we either get 0, 1, or 2 real roots, which means that we either get 0, 1, or 2 x-intercepts, one for each of the real roots. Now what about the vertex? The vertex happens at the point hk. But how do we find the values of hk when it's not given in that form? Well, we saw that when we built the quadratic formula, h equals negative b over 2a. We didn't have much use for that then, but now we can use it as a quick way to find h. But what about k? How do we find the k value? Well, once we know that x equals h at this point, we can find k because we can evaluate our function at h, the same way that we would find the y value of any point, not just the vertex. So we get that our vertex is at hk, and we now have a quick way to calculate what hk is. One more thing to keep in mind when we graph a quadratic equation is that the graph is symmetric across the line x equals h, the vertical line going through our vertex. This is called the line of symmetry.